Welcome to this lecture of network analysis and synthesis. In the previous lecture, we discussed about obtaining Laplace transform for a unit step. Here we will take another example for obtaining Laplace transform, and that function for which we will get Laplace transform is e to the power at. Now, using the definition of Laplace transform, if we find out Laplace transform of this any ft, then it is 0 minus to infinity ft e to the power minus st dt. Here our ft is equal to e to the power at, so it will be simply 0 minus to infinity e to the power at e to the power minus st dt. This can of course be written as 0 minus to infinity e to the power a minus s t dt, and this we can of course write as e to the power minus times s minus a dt, and it can be written as 1 upon s minus a. This is the derivation for Laplace transform of a function which is e to the power at. But there is one restriction, there is one condition on this solution, this result which we are getting, and that is that sigma 1 should be greater than a. What is this a? This a is this a. And what is that sigma 1? That sigma 1 is the same sigma 1 which we discussed when we were discussing about the definition of, not the definition, the sufficient condition for this ft to be transformable. That was it mod of ft into e to the power minus sigma 1 t dt should be less than infinity. So here the sigma 1 which is used, that sigma 1 should be greater than a. We will come to this later on when we will be discussing about inverse Laplace transform. But now let us summarize the results we have obtained so far. So this gives us a transform pair that is e to the power at and 1 upon s minus a. This is one transform pair. And in the previous class we have got transform pair ut, and its transform was 1 upon s. So thus we have got so far two transform pairs. This is ft and this is fs. These are transform pairs we have derived so far. Now we can talk about inverse Laplace transform. So inverse Laplace transform it's a complex inversion integral. Why complex inversion integral? Because we have got now fs, where s is a complex quantity. This s is a complex quantity. So now if you want to get inverse Laplace of this f of s, then it is going to be f of s e to the power st, and this dt term will be ds. This is no longer real, this is complex, and our limits of integration will be for s, which is complex. So limits of integrations will also be complex. Now here if we see limit of integration, then it will be having this real part fixed, and variation will be there in the imaginary part. So it is going to be from minus j sigma to plus j sigma. So our limits of integration are having constant part unchanged. Complex imaginary part is changing from minus j infinity to plus j infinity. So our complex limits are given here. Over this we are going to do integration to obtain our ft. This gives us ft. This is inverse Laplace transform, and this integration is called contour integration. And here the path of integration, which keeps this real part constant, and we vary from minus infinity to plus infinity on imaginary axis. That path of integration is known as Bromwich path. Bromwich path, and it is along the vertical lines So how it is along the vertical lines? So it is like this. So our axis of complex plane S are like this. It is 0, 0. This is minus sigma. This is plus towards plus sigma. And this is our j omega axis. This is minus j omega axis. And the sigma 1, which we have seen earlier, this sigma 1, which is present in the sufficiency condition. This sigma 1 is somewhere here. And this is our path of integration, and it is going to sigma 1 plus j infinity. And this side it is going up to or it is going, we can say as it is path of integration. So from sigma 1 minus j omega j infinity to sigma 1 plus j infinity. And so its name is path of inversion integral. And as we have seen earlier, that if you take Laplace transform of e to the power at, this comes out to be 1 upon s minus a, with a condition that this a should be less than sigma 1. So this a1, sigma 1 is this one, and a should be less than sigma 1. So if a is less than sigma 1 means that will be between these two lines. So we can get one value sigma c less than this, and this value where it is cutting is sigma c, and this line is called as abscissa of convergence. Now for this integration, this is inverse Laplace transform definition. For proper evaluation of this part, we require that sigma 1 is greater than sigma c. Now the fact that sigma 1 may be chosen greater than sigma c is equal to a. This fact implies that the transform fs exists since minus 0 minus sufficiency condition e to the power minus sigma 1 t dt is less than infinity is satisfied. So Here we will stop, and then we will discuss the next topic in the next lecture. Thank you.